All right, so where we left off was we saw that this set C, which is the set of initial conditions that can be driven to the origin, is a vector space. And we're hypothesizing that it's a vector space that's not all of Rn. So in particular, it's going to be a vector space and its dimension has to be strictly less than n, because any vector subspace of the whole space has to have a dimension, and that dimension, if it's not the whole set, it's going to be strictly lower. So it's going to have some dimension r, which is a subset, which is less than n. So in particular, so C has a basis. That is, i.e., C is equal to the image of R vectors. 1, VR, where this matrix, V, it's going to be an N by R vector, where, so C is this thing, it's an N by R vector, where R is the rank and R is strictly less than N, just by the construction that we have. All right, cool. So what we know from last time is, what we know from earlier in the lecture is there exists an X that is not equal to 0 such that X transpose V equals to 0. Because this is a rank R matrix where this is a rank R matrix where this is a tall matrix. R is strictly less than N. So this is what we saw earlier in the class today. We've got this matrix with fewer columns than it has rows, and it's full rank in that R. That tells us that this thing, there's a non-zero vector such that if I hit it on the left, it is equal to 0. All right? And so that in particular tells me for anything, so how did we construct this C? Anything in this set C is always going to have this form, 0 to Tf e to the minus a t b ut. Everything in this set C has that form. And everything in this set C, there has to be some thing here. I'm going to call this thing, because it's in the image of this basis. What that means is that for any u that I put over here, there's going to be some z. There exists a z. Let me write this z a little bit better. There exists a z so that this thing is equal to that. And what we saw before here is that this thing, this is going to tell us that z transpose of this guy, which is equal to, well, x transpose that, x transpose vz. So x transpose this is equal to x transpose that, because we know that this thing is in the image of this set of vectors. So what is this thing based on that what we have over here? It's equal to 0. And so this is telling us over here what we've just seen from that basic fact from linear algebra is that for any input that I can put in here, so i.e. for all inputs, x transpose e to the minus at b ut dt is equal to 0 for all possible inputs. And so that actually means that if this is 0 for all possible inputs we could ever put in, the only way that that's going to be true is if this is 0 for all time. This implies x transpose e to the minus at b equals to 0 for all t greater than or equal to 0. That's what it's actually going to be telling us here. This is up to Tf. All right, so that's what we've got. So what we've just shown, let's just recap the argument of what we showed over here. What we said is that the things looking like this form a subspace. That subspace has a lower dimension, so that means that everything in this subspace can be represented as an image of this finite collection of basis points, where this collection of basis points there are of them. And what I can do is, by that orthogonality principle, because it's not the whole space, I can find something orthogonal to all of those. And that's what we actually showed earlier in class, is that I can find something orthogonal to that basis, that matrix of basis vectors. Which means that for every u, this thing is equal to 0. Which means that for every time, this thing is equal to 0. Now let's see that that's going to show that what I'm going to end up showing is that this x times this matrix, x transpose times that matrix, has to be 0. So we have that x transpose e to the a t b equals 0 for all t greater than or equal to 0. So in particular, what we're going to show is that all of these guys have to be 0. So specifically, t equals to 0. At t equals 0, what is this thing going to be? That's right, the identity. X transpose e to the minus a 0, b is equal to x transpose b, which is equal to 0. Cool. Now, what we know is that if this thing is 0 for all time, its derivative has to be 0, right? And in fact, if it's equal to 0 for all time, all of its derivatives have to be 0. And because this is 0 everywhere, we must also have d dt x transpose e to the minus at b is equal to 0. And so what's the derivative of this thing? Well, the only thing that depends on time is this thing right over here. We take the derivative of that thing, we're going to get this thing is equal to minus x transpose a e to the minus at b, right? And what we can do is we can do the same trick like we did before. We plug in t equals 0. We evaluate this at t equals 0. Evaluate this at t equals 0. This is equal to minus x transpose ab. So we can see that x transpose ab has to be 0 as well. And now we could keep doing this, right? So in particular, d squared dt squared x transpose e to the minus atb, because this is identically 0. So the only way it's identically to 0 means all of its derivatives have to be 0. So this thing is actually going to be, take derivative of this thing twice. Derivative of this thing twice, we're just going to get left with x transpose a squared b, evaluated at t equals 0, e to the minus at b, evaluated at t equals to 0, it's x transpose a squared b equals to 0. And we can just continue on in this fashion. And what we found is that x transpose, after some, continuing this pattern, we're going to see that x transpose a to the k b is equal to 0 for all k greater than or equal to 0. And so that's going to imply that x transpose b, ab, a, and minus 1b is actually equal to 0. All right, cool. That's that. We're going to do just a few more things in today's lecture. One is we're going to revisit that matrix that we saw before. So we're going to discuss controllable canonical forms. So the main thing that we're going to show in this part about controllable canonical forms is that, say, system defined by A, B is controllable with B in R n by 1. So meaning this is a controllable system defined by this A, B, and we've got a single input, i.e. single input. You can extend this to the multi-input case, but it's just not very, like, it's not the most helpful thing in the world. So what we're going to do here is we're going to go and show that we can always find a change of coordinates that brings us to a form. So we can find there exists a matrix. I'll call this a matrix T, such that T inverse AT is equal to 0, 1, 1. So we're going to have these zeros up in here and the ones over in here. So this is our companion matrix. We got zeros above this diagonal and zeros below this diagonal. And then an A0 minus A1 all the way up to minus A n minus 1. So this is our companion matrix that we saw in the beginning of class. And T inverse B is equal to 1, 0, 0. Now, let's for a moment see why this thing is controllable. Yeah, let's go and see why this thing is controllable. Well, I mean, the big thing that we're going to see here is that the controllability matrix. So let's call this thing A hat equals to B hat. So what is going to be B hat, A hat, B hat, A hat, n minus 1? I need to put this thing down in here. Sorry about this. 0, 0, 1. So it's actually important that that be down there. Sorry about that. There are two different ways that people sometimes write the controllable canonical form. Sometimes they put the B up at the top and this thing over here, and sometimes they put the 1 at the bottom and put this thing down here. Let's go the other way around. Should be this thing 0 all the way down to 1. So this thing is going to be equal to, the first one is 0, 0, 1. Now the next one is going to be, just pick off this thing. So in particular, it's going to pick off this column here. So it's going to be 0, 1, 0. Well, it's not 0, it's something. It's going to be this negative A star, but it turns out that I'm not going to really care about what that thing really is, because I know if I need to figure out what the next one is, so this is B hat and this is A hat B. The next one is just going to be A hat squared B hat. So I'm just going to have to take this thing and hit it against this thing over here. And what's going to happen is the first thing that's going to pick off a non-zero thing is going to be when we hit this 1 up into here, right? This 1 above this in the third row up. And so the first thing hits the 1 in the third row up means it's going to go 0, 0, and it's going to hit a 1, and then it's going to be something, something. So we got zeros above here, zeros above here, and we're going to continue in this pattern where what's going to happen is we're going to get 1s in the anti-diagonal and stuff here, and I don't really care what that stuff is, because if I looked at this thing, what is the rank of that thing? It's n. That's right, it's n, because I can always, I can't change the rank. The rank is the number of linearly independent columns. And I could just shuffle the columns around and get an upper triangular matrix with 1s along the diagonal. So that means it's got rank n. Okay, so this representation of the system is what's called the controllable canonical form. And we actually saw this earlier in class when we were looking at realizations of systems. When we gave you that formula for given a transfer function, here's the realization, the A was this thing and the B was that thing. We got exactly that, right, when we did our realizations. Just look back in your notes if you don't remember it. So what we're going to show here is we're going to basically figure out how to find that T matrix. So let's go and do this. So in particular, the way we're going to do this is we're going to go and write down that this thing is actually, let's just go and see what's going to go on here. So in particular, what I'm going to do is I'm going to look at A times the controllability matrix, and we're going to simplify this thing out here. It's A times B, A, B, A, n minus 1B. Now what I can do here is, this is a trick that we're going to see all the time when we're dealing with matrices, block matrices. What we can do is we can take this A, we can pull it to the inside on each of these columns. So we put the A over here, put the A over here, put the A over here. What we're doing is we're just raising all of the powers to, by 1. So what we get is, we get AB, A squared B, AN B. Now, what was the theorem that we used to say, okay, if I have something that's power n, how can I express it in terms of all the lower order powers? It's the Cayley-Hamilton theorem. That's right, Cayley-Hamilton. The Cayley-Hamilton theorem says that AN plus AN minus 1 like this, n minus 1, A1, where these are the coefficients of the characteristic polynomial. A0I, this thing is equal to 0. All right? And so I'm going to use this fact to go and rearrange this thing a little bit. This thing is actually equal to B, AB, and I'm going to pull something off to the right over here. B times, now let's see what this is actually going to have to be. If I want to pick off, if I want to hit this thing, I'm going to try to figure out what are all the columns of this matrix over here to make, what do I have to hit over here to get this matrix. So if I want to pick off this particular column, I'm just going to pick off that thing right here. So I'm going to get a 0, 1, and then zeros everywhere else. If I want to pick off this thing, I really need to pick off the third column. So I need to do something like this. And if I wanted to pick off the n minus 1 thing, I really need to pick off the, if I want to pick up the n minus 1, which is the thing that's going to go over here, so we're just going to use this pattern here. I'm going to pick off the last, I'm going to pick off the last one of this to get the n minus 1 showing up over here. And then the final thing is to say, so we're going to get a 0, is to say, okay, how do I get this an? Well, I can express this an in terms of all of these lower order powers by just using that Cayley-Hamilton theorem over there. In particular, I'm going to get a minus a0 and a minus a1 here, all the way down to a minus an minus 2 and a minus an minus 1. And what is this matrix that we just constructed over here? This matrix is just the transpose of the companion matrix. So this is where I confuse myself. Sometimes they call this the companion matrix, sometimes they call this the companion matrix. But this is just the transpose of this companion matrix that we constructed over here. This thing where these are the coefficients of the characteristic polynomial of this original matrix A. All right? And so the thing that is interesting about this, so this thing is just equal to A hat transpose, is that you notice here that we can summarize this as AP is equal to P A hat transpose. Cool. We've got AP is equal to AP hat transpose. Now, notice that this matrix only depends on the characteristic polynomial. Notice it doesn't depend at all on B. B is here, but this matrix A hat, no dependence on B whatsoever. No dependence at all. So let's go and think about this. What is the characteristic polynomial of A hat that we've constructed over here? It's just the same exact characteristic polynomial as the original matrix. So what we have is we have A P is equal to P A hat transposed, and if P hat is equal to B hat, A hat, B hat, A hat, n minus 1, B hat, if B hat is equal to that, then what we have, because this matrix and the original A hat have the same exact characteristic polynomial, we must have that A hat B hat is equal to P hat A hat transposed. Yep, that's what we've got, because again, if I took this thing times the controllability matrix is equal to controllability matrix times the transpose of that characteristic polynomial. And so if I want to go and figure out how I can get a transformation that brings me from this guy to this guy, well, I just kind of solve this, right? I'm going to have I'm just going to say that A hat. So by construction, we're assuming that the original system was controllable. We had that this guy, this P, has to be invertible. And if this thing just by construction, it was controllable, we saw that. So we can see that A hat is equal to P hat, A hat transpose, B hat inverse. And A hat transpose is equal to P inverse A P, like that. So what I can do is I can just plug this thing into here, leaving me with P hat, P inverse A P, P hat inverse. I'm going to call this guy T, and indeed, this is its inverse. Because if I went and I hit this by that, these things are going to cancel out and that thing is going to cancel out. So this is indeed the inverse of that. And finally, so what we saw here is we got this transformation that gets us to this controllable canonical form. And then we're also going to have that, recall that B hat was equal to 0, 0, 1. So what I want to show here is that T inverse B, well, let's go and think about what this T inverse really is. Let's plug in what T inverse is. It's P hat P inverse times B. But B is actually going to be the following thing. It's going to be P hat times P inverse times B, AB, A n minus 1B times 1, 0, 0. There's just a little bit of trickery here. I can look at this matrix, this vector B, and I can pick it off by just putting a 1 here and zeros everywhere else. And so, what is this thing? This thing's actually P. And so what we get left with is that this is equal to, if I plug in the value of B hat, or the value of P hat, by our construction that we have up here, B hat, A hat, n minus 1, B hat, 1, 0, 0, we get left with B hat. And there we go. So there we have our construction that T inverse AT gets you to the companion form, and this T inverse B gets you to this 0, 0, 0, 1 vector. So that's a transformation that, given any controllable system, we can construct in order to put us into this controllable canonical form, where this guy's a companion matrix that's 0, 0, 0, 1, and this thing by construction tells us that it's a controllable matrix. It's a rank n matrix. Okay, cool. So last two facts that we're going to do. Sorry, this is going to be a very fast lecture just because they're kind of going to lump in the Thursday and Tuesday, I think. So the last thing that two things that I want to talk about are what happens if a thing is not controllable. So we're going to decompose this. This is going to be another decomposition of the system. So say the system is not controllable. So rank B, A, B, A, n minus 1, B. So in this case, I'm not going to be worried. This dimension of B, we're no longer assuming it could be single input anymore. So B in R n by Q. We're going to assume it's something like that. All right. So general. This is general case, and we're going to assume it R less than n. What I want to do is I want to show that we actually are going to have a transformation. We're going to find V such that V inverse AV is equal to A11 hat 0. This is going to be of dimension R. This is dimension n minus R. This is of dimension R. This is dimension n minus R. A12 hat. A22 hat. V inverse B is equal to, this is going to be of dimension R. This is dimension n minus R. V1 hat 0. N minus R. So we're going to get another change of coordinates that's going to isolate the controllable piece. So this is going to correspond to the controllable piece, and this is going to correspond to the uncontrollable piece. Okay? So let's see why that is true. All right. So let V1 through VR, and I'm going to call this equals to big V1 be a matrix of basis vectors for the image of B, A, B, A, n minus 1. So this is a basis of this image. In particular, you could always construct this by finding R linearly independent columns of this matrix. Because remember, the rank is the number of linearly independent columns. So if it has rank R, there have to be R linearly independent columns. So we can just pick R linearly independent columns of this thing, and we're going to get this matrix. And we're going to let V2, big V2, V R plus 1, V n be such that, remember, if we took any basis of some subspace, there's always other vectors that we could take to complete this to a full basis of the original space. You could do this by classic techniques like Gram-Schmidt orthogonalization. You've probably seen that at some point in life. So we can always complete this set of linearly independent vectors to a basis of the whole space, such that V1, VR plus 1, Vn. So if this is a basis of the whole space, which is equal to V1 big V2, is invertible. So what we can always do is if we've got our linearly independent vectors, we can just take some more vectors that are independent of all those and construct ourselves a basis of the whole space. All right, cool. So we've got this thing. Now, first off, I want to say that anything in the image of A, okay, anything in the image of A is actually equal to anything in the image of, so let me take a step back here. What I'm going to show here is that, which is the image of P, that the image of AP is actually contained in the image of P. All right? So what that's going to mean here is, in particular, this is going to imply that for all V1 through VR, A VI is in image of P, which the image of P is actually the image of this V1 by its construction. V1. That's what we're really going to show. And we'll see why that's important here in just a second, but let's see why this is true real quick. So, in particular, what we know here is that AP is equal to, by what we saw just earlier in the lecture here, it's equal to that thing, right? We saw that where this is the companion matrix. Well, if it's single input, it's the companion matrix. If it's not single input, it still works. But what we see is that it's actually this. AP is equal to AB. In general, we can't use the companion matrix because this could have higher dimensions. B. And then this is going to be A n to the B. But we can use the Cayley-Hamilton theorem again for this thing. So it's AB, A squared B, A n minus 1 B times negative K equals 0 to n minus 1 AK times B. All right. So we have AP is equal to that thing. And so, in particular, if we took anything on the right here, what we can see is we can always express all of these columns. There is some matrix here that we could multiply on the right. It's just going to be the companion matrix, but with identity matrices everywhere else. So it's not exactly the companion matrix. Identity matrices where we put ones. It's just worked out so that the dimensions are correct. There is going to be some matrix where this is actually P times M for some matrix. It is literally going to be just the companion matrix, just where instead of ones you put identities, instead of zeros as just single zeros, you're going to put zeros that are of appropriate size. In particular, they're going to be Q by Q zeros. So it's actually the Kronecker product of the companion matrix with the identity matrix of Q, if you want to work out things in terms of Kronecker products and you feel like that. You don't have to. It's just what it is. I don't think we really need to go into that whole detail. But the key thing here is that if I am going to take anything in the image of this AP, so the image of AP is just going to be stuff like this. So Z in image of AP, if and only if there exists an X such that this is just what the image is, AP X, which by the construction that we had before, this is actually going to be equal to this thing up here for that matrix M that we got using the Cayley-Hamilton theorem. And so this thing is going to be, this tells us that Z is in the image of P. All right. So what that means here is, in particular, using this fact is what we mean by the images, which is equal to the image of V1. So in particular, what that's going to tell us is that A times this V1 vector, because all of these guys, this is every column of this, Vi is in the image of P for I equals 1 up to R. That's how we've constructed this thing, where this thing is just the first R, this V1 is just the first R of these things. This implies that A Vi, by what we had over here, is in, so this is just taking something from that image and then mapping it through A. It's still in the image of V1. And so this tells us that there exists A hat I1 up to A hat IR such that the way I'm writing this is not the best way in the world, such that A Vi is equal to V1 A hat I1. I'm going to just write different letters here just to not confuse the issue. Z1I, Z1, ZRI, sorry about this, R1I down to ZRI, like that. Because this thing is in the image, which means there has to be something over here that satisfies this. Now, doing this for all of the columns in this V1 matrix, what this actually says is that we can find a matrix like that. Because each column of this guy is just going to correspond to one of these guys over here. Okay, cool. So we've got that. And finally, we're going to have a V2. This thing, each column of this thing is in Rn. Now for everything in Rn, there's always going to be something on the other side that makes this true, because this guy, this matrix, the columns form a basis of Rn, so we can make this be A12, A22 hat. For some matrices, A12, A22. And the reason is just this. This is a basis of Rn. The columns form a basis of Rn. So that means that no matter what these things are, so this is actually just an invertible matrix, right? This thing over here. So no matter what this thing is, I can always just hit both sides by the inverse, and I'm going to get this A12 and A22. Right? Because this is just equal to V1, V2, inverse, A. V2. That's just all that is. Just building the columns of this thing. So in summary, what we've gotten over here is that A, V hat 1, V hat 2 is actually equal to V hat 1, V hat 2, A hat 1, 1, 0, A hat 1, 2, A hat 2, 2. Looks like that. So all I'm doing is I just took this equation and stacked them up. So we've got the first piece now. And finally we're going to get that second piece. And the second piece works out really, really similarly. And it's just because image of B, because B is just one of the, it's just a submatrix of this thing. It is contained in the image of P, which is equal to the image of V1. All right? And so that means there exists a matrix B hat 1 such that B is equal to V1 B hat 1. And of course, I can just do the following bit of trickery. I can put the V2 in here. And what would I need to put down in here to make that work out? Just a 0. And so what we've shown here, if you just go and hit this on the other side here, what we have is, this is going to tell us that V1, V2, inverse A, V1, V2 is equal to A hat 1, 1, A hat 1, 2, 0, A hat 2, 2. And the last thing that we're going to see here is, again, taking this to the other side, V1, big V2, inverse B must then be equal to B1 hat 0. Like that. So the construction of this is actually very simple. You just take this guy to be a basis of this just be a set of linearly independent columns from here. This guy to be anything else that can turn this into a full rank matrix or an invertible matrix. And there we have our coordinate transformation. And this leads us to the very last thing that we're going to show, which are the PBH rank tests. So if it's not controllable, we can always find a coordinate transformation that looks like this. Now the final thing that we're going to deal with in controllability is PBH test. So these are people's names, but I don't actually remember all the names. It's in the book. Controllability. Which is that rank of B, AB, A, n minus 1B is equal to n if and only if for all lambda in the complex plane, A minus lambda I, B is equal to n. All right. So sometimes this test is just a little bit easier to use than the controllability test. And so let's just do one example of this where, well, we'll just go through it and we'll deal with these things in homework and stuff. So this one's just kind of easier to show formally. So, and the way we're going to do this is we're going to do contrapositive on both sides. We're going to say this isn't, say that this isn't full rank, then we'll show that that thing is equal to 0. And we'll say this isn't full rank, we'll show that that thing, we'll show that that thing's not full rank. So in the one direction, we're going to say this is not full rank, then we'll show that that's not full rank. If rank of A minus lambda I, B is strictly less than n, what do we know is going to happen here? Because if this is dimension n, if this thing has rank strictly less than n, that means this thing's also going to have n by, it's going to be n by n plus q if this was n, q, n. Over here, if those are the dimensions. That's going to mean that for some lambda, that's going to mean that there exists an x not equal to 0 such that x transpose A minus lambda I B equals to 0. But this thing is actually equal to x transpose A minus lambda I x transpose B. And so both of these guys are going to have to be 0, i.e. x transpose A equals to lambda x transpose equals to 0. Well, no, we don't need that that's equal to 0. All we need to do is, all I was doing here is by setting this thing equal to 0, we get this eigenvector condition. It's just a left eigenvector, and x transpose B equals to 0. That's what this being equal to 0 is equivalent to that. This being equal to 0 is just that. And so this is going to tell us then that x transpose AB is equal to lambda x transpose B, which is equal to 0, x transpose A squared B. You just apply this equation twice to get lambda squared x transpose B equals to 0, and we just continue this process to see that x transpose AK to the B is equal to lambda to the K x transpose B, and it's equal to 0. And so, in particular, if I'm going to hit this thing on the left with x, I'm going to get it to be equal to 0, implies x transpose B is equal to 0, implies the rank of P is left. All right, cool. So we just showed that. Now the other way, it's going to be a little bit different, but we're just going to use that little bit of trickery that we saw from last time. We're going to use that decomposition that we saw. Now I'll say rank of B, A, B, A, n minus 1B is less than n. What this is actually going to tell us here is there exists a V invertible such that V inverse A V is equal to A1 1 0 A1 2 A2 2 V inverse B is equal to B1 hat 0. And so what we're going to get is we can just go and rearrange this thing to see that A minus lambda I times B. What I'm going to do is I'm going to just go and rearrange this thing a little bit so that I can say that this thing is actually equal to, if I call this guy A hat, and I call this guy B hat, I'm going to say that, hey, this guy is actually equal to V A hat V inverse times V B hat. And let's go, oh, minus lambda I. I can pull that lambda I in here, sorry. Lambda I. The inverse. So the reason I can pull that thing inside is just the hat. The reason I can pull that inside is this times this just cancels out and gives us the identity. And I can simplify this down one more time. A hat minus lambda I B hat all times the inverse. Well, this thing times the inverse. Alright, so all I did was I just plugged in my expression for this thing over here, because this thing is going to tell us that A is equal to V A hat V inverse. Alright, now let's go and look at this a little bit further. A hat 1 1 0 minus lambda I A hat 1 2 A hat 2 2 minus lambda I B hat 1 0. that's just plugging in what these guys are. Quantity B inverse. Just regrouping the terms here. All right, let me write that a little bit more neatly. B hat 1, 0. Okay, now let's see how we can actually find a vector x such that we can hit this thing on the left and make it go to 0. So in particular, there exists x2 not equal to 0 such that x2 transpose A hat 2, 2. There is a non-zero vector here and lambda complex. So if this is any eigenvalue eigenvector pair, we're going to have this, where this is just a left eigenvector. But of course, a left eigenvector, you can find it by just finding the eigenvectors of the original matrix transpose. So namely, I can always find an eigenvalue eigenvector pair of this matrix down in here. That's the key thing that we're going to be dealing with. So what we have in particular is 0 x2 transpose V inverse times A minus lambda I B hat B. So I'm taking this vector here and multiplying it on the left. Taking this vector, which I constructed as an eigenvector of this A22 thing, and I'm multiplying here on the left by this V inverse. The reason being here is that, one, I know if this is non-zero, this overall product has to be non-zero because it's a non-zero vector times an invertible matrix. And what's going to end up happening is when I plug this thing into here, this guy's going to hit with that guy and cancel out entirely. And so in particular, I'm going to get left with, when I cancel out with this thing and bring it on inside, I'm going to get a 0 x2 transpose A11 hat minus lambda I, 0 A12 hat A22 minus lambda I. This whole thing times B inverse. But what's going to happen is this hits with that, we're going to get a 0. This hits with that, we're going to get a 0. This hits with that. Because this is an eigenvalue eigenvector pair, that's going to go to 0. And then I'm not going to be able to fit that matrix in over here, but it is going to be x2 transpose B1 hat 0. And so we can see that this thing goes to 0. And so this thing needs to be hitting with that thing over there, and we're going to get a 0. So that was a little bit messy how I wrote that. Let me just do it again up here, a little bit more clean, a little bit bigger. 0 x2 transpose V inverse times A minus lambda I B is equal to 0 x2 transpose V inverse times B. So just plugging in that derivation that I had before here, I'm just redoing this more neatly. A12 A22 hat B inverse B hat 1, 0. This is going to cancel out, and I'm going to bring this one on either side. I need to have a minus lambda I and a minus lambda I over here. So it's going to be 0 x2 transpose A11 hat minus lambda I, 0 A12 hat A22 hat minus lambda I times V inverse times 0 x2 transpose B1 hat 0. Alright, and so as we saw, just more slowly this times that is 0 plus this times that is 0, this times that is 0 plus this times that, which by construction that's 0, so this overall thing is 0. And then same deal, this times that is 0 plus this times that is 0 is 0. And there we go, so we have it. And alright, so that's it. Cool. There's a lot smashed in, but it's just because I'm going to be gone, so we need to do something about that.